Hello friends, today we are going to see Calixarenes. I am Dr. Gerald Anthony, Assistant Professor in Chemistry, St. Xavier's College, Palayamkottai. So the Calixarenes are a group of macrocyclic supramolecule, which is formed by the condensation reaction between para-substituted phenol and formaldehyde. So it is more or less like a bridged aromatic ring. So since it is a bridged aromatic rings, they come under the category cyclophane family. So the name Calixarene was given because it resembles a Greek vase known as Calix crater. This is Calix crater. So this is a simple Calixarene. So usually the Calixarene, there will be a number will be mentioned in the square bracket. The number is nothing but the number of aromatic ring or phenyl ring present here. So here you can see 4 is represented here, 4 aromatic rings are present here. So usually the structure will be mentioned in the cyclic form. So for example, one phenyl ring will be mentioned in this way. So another phenyl ring will be mentioned in this way, another phenyl ring will be mentioned in this way, and the another phenyl ring will be mentioned behind. So in this way it will be more or less like a round table in which in four corners four persons are sitting. So we are viewing that round table from the one point of the from the viewpoint from the one of the person. For example, if four persons are sitting here, we are viewing that whole round table from this person. So in the same way, four phenyl rings are situated in a cyclic manner. So we are viewing it from the one of the aromatic ring present here. So for example, we can say we are viewing from this aromatic ring. This is here. So remaining two aromatic rings will be appearing in the peripheral position, and another one aromatic ring will be in the eclipse position. So only I have represented it in black color. So next we are going to see. So the name maybe can be also given like that. That is, this name is para tertiary butyl. So in para position there is tertiary butyl. So it is known as since it belongs to Calixarene family, Calix, and since the arene rings, that is aromatic ring, there are four arene rings. So four arenes. So this is the way we can represent it. So the Bakeland, a scientist, was able to produce a homogeneous, highly cross-linked phenol formaldehyde resin known as bakelite, and this bakelite here, this bakelite will undergo cyclization. This is the bakelite structure. So it will undergo cyclization using isotope dilution method. So it will leads to this Calixarene. So in this Calixarene, you can see that in para position there will be methyl group. So for a Calixarene, it is very much must that there should be a para substituted phenyl group, phenol, and a formaldehyde group. Okay, it should be that. This is a para tertiary butyl Calix 4 arene structure. So So here you can see the tertiary butyl rings are orienting to in this way. So the 4 tertiary butyl rings will be oriented in upward or downward. So if it is oriented upwards, then OH groups will be oriented downward. So in between the aromatic ring will be there. So we can see. So the conformation is for para tertiary butyl calixarenes, it is more or less for all the calixarenes when the alkyl groups are the phenolic group, if all are oriented in upward position, then it can be called as cone conformers. If 3 are in the upward position and one of that aromatic ring is oriented totally opposite to the 3 rings, then it can be called as partial cone. So another one is one to alternate conformer. So one to alternate conformer means here the first aromatic ring and the second aromatic ring will be having similar conformation. So it may be having the alkyl groups above the plane, and the 2 aromatic rings will be having inverted position in which it will be having the aromatic rings downward. Sorry, the alkyl groups in the downward position. For example, if I am drawing for one to alternate. So here I am putting one OH, another OH upwards. Now I am going to draw for another one. Here the OH will be downwards. In same way I am drawing for another one also. Here also the OH will be downwards. 2 OH, sorry, OH or alkyl group, any one thing. Here you can say that alkyl group. So here the alkyl group is upwards. Here the 2 alkyl groups will be downwards. So this is one to alternate. So obviously if the alkyl groups is in the upward position, then OH groups will be in the downward position. So it will be conversely true. So it will be converse, it will be present straight opposite to that of the alkyl groups. In 1,3 alternate, first aryl group will be having alkyl group in the up arm or upward orientation. Second will be downward. Again third will be upward and fourth will be downward. So this is known as 1,3 alternate conformers. So here some of the Calixarenes are given. So as you already know, there is only one structure which is going on repeating. So you will be having this one structure going on repeating for 4 times like a polymer. So here we are having n values equal to 4, so we can write it simply like that. So here this is an alkyl group, so it is represented as R. Here you cannot say only phenolic group will be there. There may be some substituted methoxy groups or any other alkoxy groups may be also there. Only one thing needed is it should have it should possess an oxygen atom. So it may be methoxy like alkoxy groups, and in para positions it may have alkyl groups. Okay. So another important thing, so some of the calixarenes which we use in our present study will be here tetramethyl calixarene, in which R will be H and Y will be a methyl group, that is tetramethyl ether calixarenes. So here the 4 is used to mention the number of aromatic rings. If suppose if R is a tertiary butyl, Y will be a methyl group, then it is para tertiary butyl tetramethyl ether calixarenes. So next one is, if you are having R group hydrogen, it is having hydrogen and Y will be N-propyl. It may be tetra N-propyl ether of Calixarenes. So there are three types of Calixarene which we will be used to study the supramolecule Calixarene. So next, and this is cation complexation of Calixarene. Here they are taking a Calixarene like simile. So it will be having a hydrophobic pi binding pocket. That is, it will be having aromatic ring. It will be the 4 aromatic ring present in a cyclic way. So the 4 aromatic rings will be present in a cyclic way attached with a CH2 linkage, and here behind it will be having spheron like uh, it will act as a spheron like guest binding site. So it will be more or less like a spheron like guest binding site, and it is known as lower rim. This position is known as lower rim, and it is known as, it is wide and it can be called as upper rim or upper substituents. Okay, so for as for the most of the Calixarenes, the phenolic group or the alkoxy groups will be present in the lower end. So it will be, so here it will be having phenolic groups or alkoxy groups. So it will be behaving more or less like the para anisyl groups present in the spheron. We have already discussed about the spheron. So it will be behaving like a anisole. So here you are having, so these are OH or alkoxy group. So it will be behaving like a para anisyl groups present in the spherons. So it will be in spherons, it will be very rigid even in the solution state. Same type of character will be existing here. You can see. So here this 4 oxygen atom is binding this guest very strongly. That is the meaning. So it is like a spheron like guest binding site, guest cation binding site. So the guest may be usually cation, so it is given as guest binding cation site. So this type of behavior is usually noticed in the para tertiary butyl Calixarenes when it is allowed to react with a mixture of sodium benzoate and one equivalence of water and triethyl aluminum. So here now what happens, the sodium ions will be accommodated in this spheron like guest binding site of oxygen atoms. So it will be in the lower rim of the Calixarene. So sodium atom will get bound into this lower end by the oxygen atoms present in the para positions of the aromatic ring. So you know it will be having oxygen atom in the para position, that is, it may be having phenolic group, and in another position, in para position, it may be having alkyl groups like N-propyl or even hydrogen. So this sodium ions will be attached to this Na plus. So it will be bound by 4 Na plus, sorry, 4 oxygen atoms. Since a Calixarene will be having 4 aromatic rings, it means it will be having 4 oxygen atom. So it can, this 4 oxygen atom can bind the cations like sodium effectively. Next, uh, so you can see it looks like that sodium ions when bound to this oxygen atom, this oxygen atom will be having orientation like a cone like orientation. So the oxygen atom will be found to situate inside this cone like structure. So if I view it in the inverted position, it will be more or less like a cone. Inside that cone, the sodium ion will be bound. It will be resembling a cone like conformation. Actually it looks like a cone like conformation of the Calixarene. It will be giving a appearance that the cone like appearance will be more stable, but it is not like that. The cone like appearance cannot be said that it is more stable. Here the stability of the conformers, as we have already discussed about cone, partial cone, 1 2 alternate, 1 4 alternate. So in this way, so the conformer which is preferred will be depending upon the polarity of the solvent. For example, cone like isomer is more stable, or it is more preferred by the more polar species, like polar solvent is used. Okay, so here, since in the at the same time, in the non-polar solutions will be mostly preferring partial cone like structure. So in cone like structure, all the four oxygen atoms will be oriented in one position, either in upper arm or lower arm, mostly in lower rim. So it will be, since oxygen are polar in nature, it will be more polar. Cone isomers will be more polar. At the same time, in partial cone form, only three will be in one direction, and one oxygen atom will be exactly opposite conformer. It is partial cone, so it will be having polarity less than that of the cone isomers. Okay, so since it is having only three oxygen atom in one position, so it will require, so it will not be very much easy for the metal ion to bound to this. So metal ions cannot effectively bind by these three oxygen atoms, but here, since it is having four oxygen atoms, the metal ions can effectively bind by these four oxygen atoms in the complete cone structure. In partial cone structure, the metal atom binding ability will be very low due to less pre-organized oxygen atoms there. So for effective binding, there should be a pre-organization of the host. Here the pre-organization of host is lacking due to uh, uneven orientation of the oxygen atom. So next is, so here you can see, when you add metal chloride like lithium chloride or sodium chloride, sodium perchloride, into the calyx 4 tetramethyl calyx 4 ring in chloroform methanol structure. So metal complexes of lithium, since we are adding metal chloride like lithium perchlorate and sodium perchlorate, the lithium ion and the sodium ions will be acting as the guest, and it will be bind by the calixarene, and here the calixarene will be found to consist of two conformers. So it is, that is, cone and partial cone conformers, both will be present in this structure, cone and partial cone. At the same time, if the metal ion is potassium or silver, so it will be completely changed into partial cone, and 1 3 alternate isomers are observed. So why it is such that here the conformer is totally different when the metal ion changes? The main reason is lithium and sodium ion are more oxophilic. Oxophilic means it will be more oxygen, it will be having more oxygen affinity. So what happens? It will be easily bound by the lower rim, since the oxygen atoms will be present in the lower layer. So lower rim oxygen atoms will get pre-organized to the oxophilic lithium and sodium. Suppose lithium is preferring oxygen atom, automatically four oxygen atoms will rearrange themselves to bind the lithium or sodium ions. And also here, partial cone isomers also possible, not only cone conformers, partial cone conformers also possible for lithium and sodium ions. Another important thing, for silver and potassium ions, they will not prefer oxygen atom to bind with themselves, because they will directly straight away go and attach to the pi bond present in the aromatic rings. There are four aromatic phenyl rings are there. So the silver ions and potassium ion directly bound to the aromatic ring, because in aromatic ring there will be pi electron cloud. This silver and potassium ions will interact with the pi electron clouds, and it will form and bond with the 4 pi electron clouds present in the 4 aromatic rings. So this type of engagement is known as cation pi interaction, which we have studied in the types of supramolecular interaction. So here cation interaction will take place. This is the reason you can see in this diagram sodium will be present below in the lower rim, and silver will be present in the upper rim. This is due to the cation pi interaction. Here it will be interacting the sodium or potassium will be interacting with the oxygen atom. So next you can see so here you can see when you introduce a pyridine cation. So you know pyridine cation. So this is pyridine. So the pyridine cation will also approach towards the aromatic ring. So the pyridine cation will also approach towards the aromatic rings in the Calixarenes. So the pyridine cation will be approaching towards the aromatic ring present in the Calixarenes. So automatically there will be a cation pi interaction. So this pyridine ring will be interacting with the pi electron clouds of the aromatic rings. There will be 4 aromatic rings. So this pyridine cation will interact with these 4 pi electron clouds. So now what happens, due to this the 4 aromatic rings will be orienting in the upper rim, so it will be effectively, so here you can see these 4 aromatic rings will effectively bind the pyridine ring through cation pi interaction. So due to this there will be a increase in the uh, percentage of the cone like arrangement. So here you can see after introducing this pyridine cation to the n propyl substituted group in the butyl calixarene, it is noted that the cone like conformers percentage will increase from 31 percentage to 67 percentage. The main reason is due to the orientation of the aryl rings in upper rim to interact with that of the aromatic rings. So the upper rim means upward position, lower rim means lower position. When the aromatic rings themselves rearrange to the upper rim, automatically the alkoxy group will be orienting in the downward position. So here it will be having cation pi interaction. So here also a cation pi interaction. One thing is here you are using the calixarene in which a propyl group is substituted. So we have already discussed about these 3 types of calixarene in which the propyl group substituted calixarene will show this property. Next one is tunneling effect. So silver plus ions. So once they are interacting with the aromatic ring in the upward position, slowly it will move downwards. Okay, so in this way within the molecule, then again it will move upwards. In this way the silver ion will be tunneling inside the calixarene. Tunneling means moving, okay, moving inside that calixarene cavity. So it will be very fast. At the same time the silver ions which present here, sometimes it may move away from this one molecule of calixarene and it moves into another molecule of calixarene. This is known as intermolecular cation exchange. When it is moving within the molecule, it is known as intramolecular cation exchange. So when it is moving away from one calixarene to another calixarene, it is known as intermolecular cation exchange, and this intermolecular cation exchange will be very slow, but the intramolecular cation exchange, that is moving within the inside the calixarene molecule, will be very fast. So it is moving from upper rim to lower rim, again from lower rim to upper rim. So it will be very fast it has been noticed in the H1 NMR spectroscopy. And phase transfer equilibria. So butyl calixarenes are almost insoluble in water. So they resembles the crown ethers and spherens for the application of phase transfer catalyst. So they will be they will be acting as a good transport material for cesium ions, but at the same time for other metal cations like barium 2 plus, in which the charge is very high. So in cesium, the charge, it will be monopositive, barium will be dipositive. It will not have that much effective way of transporting the barium 2 plus from one place to another place, from one medium to another medium. At the same time, it can effectively uh, transport the cesium and other monopositive cations. Okay, so with this we are completing the Calixarenes. So we can see in the next class. Thank you.